We are going to start a little summer series. I came up with some different demos and such that are relevant to things that people do in the summer. And so today we're going to talk about something swimming, and people go in water, obviously, and one of my favorite toys that I'll come to. So we want to understand about what it is that makes someone float or not float. And you might just naively think, well, heavier means you won't float and lighter means you will float. But that can't really be true, because you could imagine like a little BB that certainly won't float in water, whereas you could have a large cruise ship which is much heavier than the BB but certainly floats in water. So it has something to do with buoyancy. So what does that have to do with? So we're actually going to take a step back and talk first about gases. And there's this relationship called the ideal gas law, which describes the relationship between the pressure of a gas and the volume that it's in and the temperature that it's in. It's really simple, just shown here, that the pressure times the volume is proportional to the temperature and then times the number of particles that you have. And the temperature sort of tells you how fast the particles are moving. So this makes sort of perfect sense. And I have a little simulation here of gas particles that are in a box. And at the moment, there's 50 of these gas particles. And we have a pressure of something like 4 atmospheres. And the pressure, this is what's happening on a molecular scale. It's just that the atoms are bouncing off the walls. And whenever they bounce, they transfer momentum to the walls. And a whole bunch of them doing that at random gives us this phenomena that we think of as pressure of the gas from a microscopic perspective. So I'm just going to double the number of particles. And according to the ideal gas law, that should double the pressure. So I'm just going to go whoop. And now we have twice as many particles in there. And once it equilibrates, now we see that the pressure, in fact, has gone up by a factor of 2. And then the other thing I can do, I'm going to make the volume of this chamber about 3 times smaller just by dragging this over. And we see that when I do that, now the pressure, in fact, has gone up basically by a factor of 3. So the temperature is still the same. The particles are all still moving the same speed, so they're not going any faster. It's just that because the container is smaller, they bounce into the wall 3 times as often, so the pressure goes up by a factor of 3. So in some sense, I would say this is a really easy to understand intuitively how this ideal gas law works. OK, so now we're going to come back to one of my favorite demos. This is just an ordinary Coke bottle that's filled with water. And this is just an ordinary soy sauce packet. I put a little bit of weight on it because it's a little too light otherwise. And sorry, not soy sauce, but in this case, ketchup packet. And the thing that's relevant about this is that this is filled with ketchup, but it also has a little pocket of air at the top. Just like this is filled with water, but a pocket of air. And I'm just going to drop this in like one of my favorite toys. This is called a Cartesian diver for reasons that will become clear. And then I'm going to seal the top. And I'm just going to hand this to you, and you are going to squeeze it. Awesome.
I was expecting that to go up.
Yeah, and then just let go, and then it'll come right back up. Right? So what's going on here is that as I squeeze the container, I'm reducing the volume. Right? If you were to step on it, you'd make the volume a lot less. And that increases the pressure on the gas. It also increases the pressure on the liquid. But the liquid really can't be compressed. It's more or less incompressible. So I'm reducing the volume of the gas at the top. That increases the pressure on this gas at the top. That increases the pressure on the ketchup packet. That would increase the pressure on the liquid. It does, but the liquid can't really be compressed. The ketchup can't be compressed, but the little pocket of the air at the top can be compressed. So when I squeeze on this, I end up reducing the volume of the ketchup packet. The mass stays the same. The mass stays the same. The volume goes down. That means the density of the ketchup packet goes up. And if the density, which is mass over volume, is more than the density of the water, then it'll sink. And if the density is less than the density of the water, then it'll float. So when I squeeze this, I make it a higher density. When I release this, then the density goes down, and then relative to the water, and then it floats. So this is the same thing that happens when you are in water and you are in a swimming pool, for example. When you inhale, you float more than when you exhale. And the reason is not that you're lighter. When you inhale, you're actually heavier because you have brought in air molecules, and so you're heavier by that small amount. But your volume has increased a lot more than the mass has increased, and so your density has gone down substantially, so then you can float in the water. So you can think about that next time you are trying to swim or just enjoy swimming.